Mass spring system. A mass and spring system can be made to display simple harmonic motion, like this. When the mass is below the equilibrium position, there's an upwards acceleration, as the force due to the spring will be greater than the weight. When the mass is above the equilibrium position, there will be a downwards acceleration, as the weight is now greater than the force due to the spring. The size of the restoring force is directly proportional to the displacement, so we have the simple harmonic equation A is equal to minus kx. The acceleration is equal to minus, as it's in the opposite direction to displacement, times a constant depending on the situation, times the displacement from the equilibrium position x. Here we have the spring with no load attached, and we can call this length L, which is the natural length of the spring. If we now add a mass m to the spring, it will extend by a distance e, so its total length is now L plus e. This is then the equilibrium position with a mass m attached. We can now pull the spring down further a distance x. So this is the spring pulled down by a further extension x. I've reproduced those three diagrams here. In this case, there is a force down due to the weight of the masses, which were given by mg. There will be a force up due to the extension of the spring, which will be given by the spring constant k multiplied by the extension e. This system is in equilibrium, and so mg will equal ke. In this situation, we'll have the same force down due to the weight of the masses, mg, but now the force up is due to the spring constant multiplied by the total extension, which is e plus x. This will now be greater than the weight, so we'll have a resultant force up, which I'll call F. This force F will be equal to the upwards force due to the spring minus the downwards force due to the weight. So we can write F is equal to k e plus x, the upwards force, minus mg, the downwards force. This force will give an acceleration upwards, i.e. in the negative direction. So we can write that force is equal to minus mass times acceleration. So we can substitute minus ma for F here, and write minus ma is equal to k e plus x minus mg. Expanding out these brackets, we get minus ma is equal to ke plus kx minus mg. But here we found that ke was equal to mg, so we can substitute here to write minus ma is equal to mg plus kx minus mg. These will cancel to give minus ma is equal to kx. I can rearrange that expression to give the acceleration a is equal to minus k over m times x, where k is the spring constant, m the mass, and x the extension. I've copied the equation here for reference. But the general simple harmonic motion equation is a is equal to minus 2 pi f squared times x. So equating the two, we get that minus 2 pi f squared is equal to k over m, or f is equal to 1 over 2 pi root k over m. Also, as time period t is equal to 1 over the frequency f, we can write that time period is equal to 2 pi root m over k, where m is the mass on the spring and k is the spring constant.